Our first speaker is Jared Murray. He's an assistant professor at the Department of Information Risk and Operations Management in McCombs School of Business at UT Austin. He completed his PhD at Duke, and then was an assistant professor at Carnegie Mellon. He works on flexible Bayesian models for heterogeneous and structured data with applications to record linkage, causal inference, multiple imputations for missing data, and latent variable modeling. And today he'll give us a little bit of insight on Bayesian Nonparametric models for treatment of effect heterogeneity. So take it away. And
Thanks so much, Alex.
I will hold you to 20 minutes. And
20 minutes, okay. Good luck. Thanks so much, Alex. Thanks so much to the organizers for having me here and letting me kick this off. I have to say I'm slightly discombobulated coming up here. David says one of the speakers said food poisoning, and I'm hoping to God that it's not me. Do you know? Is it? It's not me. Yeah, so I'm going to talk today about Bayesian nonparametric models for estimating treatment effect heterogeneity. I'm going to be talking mostly in terms of my application. I'm going to be talking about a randomized controlled trial. A lot of the stuff that I'm talking about is going to hold for observational studies as well. I'll say a couple words about that. So I'm going to be talking in particular about how we parameterize our models. Okay, so how we actually, parameterize our models. Prior choice, how we actually specify prior distributions for the parameters in our model, in particular the parameters we're interested in, the ones governing treatment effect heterogeneity. And then finally, I'm going to be talking about posterior summarization, right? So Bayesian nonparametrics constitute sort of a useful suite of techniques. But at the end of the day, what we have is a very complicated object. We have a posterior distribution over functions in this case, right? So we have to think about how we're actually going to distill that into insights for our collaborators if we're hoping to do this stuff in practice. So a lot of what I'm going to talk about today was motivated by a large randomized controlled trial conducted in education, social psychology, called the National Study of Learning Mindsets. So the National Study of Learning Mindsets was a randomized controlled trial to assess the effectiveness of an intervention designed to change students' mindset beliefs. Okay? So if you're not familiar with this idea of mindset beliefs, the idea is basically that you can have sort of two beliefs about your abilities to grow and change. Either that my abilities to learn new skills are sort of fixed. I'm the kind of person who is either good at math or bad at math, and that's just unchangeable. Or you might have a growth mindset, the idea that if I'm not good at math today, I can become good at math. Right? If I study hard, challenge myself, keep pushing myself, I can actually get better and better at math. Okay? So we actually have lots of evidence that students who have a growth mindset belief will actually do better. Okay? If you believe you can acquire new skills, you can. If you believe that you can't, maybe you cannot. And by the way, we have every reason to think that people can learn math. So the National Study of Learning Mindsets, like I said, it was a randomized controlled trial of a low-cost, light-touch mindset intervention. So these students spent about an hour doing an online module. So they skipped a gym class, but that was about the only thing they lost out on. It doesn't cost the schools a lot of money, so that's good too. So a lot of the existing literature about mindset interventions was from sort of small-scale studies conducted in convenience samples. Okay, so you round up, say, 100 undergraduates at your predominantly white upper-middle-class university. You do something to them, and then you publish a paper with a tiny p-value, right? So we can all pick that to death. The National Study of Learning Mindsets was actually conducted using a probability sample of high schools in the United States. So it was designed to be nationally representative. However, the sampling plan was also carefully crafted to be able to assess treatment effect heterogeneity. So what that meant was sort of oversampling schools that were high minority schools, oversampling schools that seemed like they were lower achieving at baseline. Okay? So we're really not interested in this study. We are interested in sort of the overall effectiveness of the intervention, but we're particularly interested in the question of whether or not there are particular contexts that would make this mindset intervention more or less effective. Okay? So before this study was run, we had every reason to think that the intervention could be effective on average. And then a lot of scientific questions about whether it was more or less effective in different subgroups of students, sort of defined by the context in which they found themselves and characteristics of the schools. Okay. So in particular, thinking about overall levels of growth mindset beliefs in the school at baseline, so before the intervention, is the school doing things that sort of reinforce growth mindset beliefs? Do we have teachers that actually believe that students can grow and acquire new skills? That's important. And then overall school quality level of school quality or achievement, right? So if you're in a terrible school, maybe that's going to make the intervention less effective. If you're in a very good school, maybe these things are already sort of happening for you and the intervention actually can't really move the needle, right? It's sort of a ceiling fence. Okay? So these are sort of the scientific questions that they had. Okay? So in thinking about the kinds of analysis we want to do for this problem, we want to estimate treatment effect heterogeneity here. We want to do this in sort of a flexible way. We also want to avoid sort of an explicit model selection or specification search. right? That's why I'm going to take this Bayesian nonparametric approach. I'm going to write down a nonparametric phi that I think is kind of reasonable, and then sort of let the data determine where we go from there. Okay. We're going to have school-level treatment effect heterogeneity, potentially, that's explained and unexplained by covariates. So randomization in the mindset study took place at the individual level, so we can actually think about heterogeneity across schools that's explained by covariates we know about the schools, but also unexplained by the covariates we do not know about the schools. We might have individual level treatment effect heterogeneity that's explained by covariates, again, because we have randomization at the student level. We can't really think about heterogeneity that's unexplained by covariates, or trying to estimate that at least would be complicated. I'm actually not going to talk about that today anyway. We really want to have interpretable model summaries to communicate results, right? So there are a lot of people that are interested in the findings from this study. Most of them are not statisticians. Most of them don't know how to think about a posterior distribution over functions. I would actually go so far to say that most statisticians don't know how to think about a posterior distribution over functions, right? So we need a way to sort of distill the knowledge that's encoded in that complicated posterior and communicate it effectively. Part of communicating it effectively is also giving appropriate measures of uncertainty. So we can do all these things. We can do all these things with Bayesian nonparametrics. I have a particular Bayesian nonparametric approach that I like. I'm a little bit biased on the second author on the paper, but this Bayesian causal forest idea I think is really powerful. I'm going to talk very, very briefly about that, but I want to sort of keep my comments today at sort of a higher level. How should we be thinking about specifying Bayesian nonparametric models for estimating treatment effect? So since I only have a few minutes and you guys are probably up to speed, I'm not really going to talk about my identifying assumptions. Told you in the beginning I'll be talking mostly about randomized controlled trials. When I'm talking about observational studies, I'm going to assume that I have all my confounders measured, right? So this slide really only exists to set some notation. I'm going to use Y for my outcomes. My application, that's going to be math GPA. I'm going to use Z for a binary indicator treatment assignment. So use 1 if you got the treatment, so use 0 if you didn't. And then I'm just going to use X sort of generically for a vector of covariance. Okay? And then tau of X here is going to be the function that is giving me my heterogeneous treatment effects. Okay? Tau of X is just the conditional average treatment effect for an individual that has covariate vector X. Okay? But let's forget sort of all of that for a second. Let's actually go back to the simplest possible case. Let's imagine that we ran a randomized controlled trial. We did it very well. The randomization was perfect. And we want to think about just trying to infer an average treatment effect. Okay? So we can think about the very simplest possible model we might write down for that. Okay? Sort of this two groups model. Where we have two different distributions, one distribution for the treatment group, one distribution for the control group. In this case, I'm going to actually keep things super, super simple. I'm going to specify a normal distribution. I'm going to specify that the variance of the outcomes in the two arms is the same, and the only thing the intervention did was move the mean. Okay, so we have mu0 for the control group, mu1 for the treated group. Okay? Now, in this case, I'm just interested in estimating an average treatment effect. The average treatment effect is going to be given to me in terms of the model parameters as mu1 minus mu0. Right? That's the average treatment effect. And if we do sort of the naive thing and just specify independent normal priors for the two group means, okay, with mean phi0 or phi1, and then prior variance delta 0 or delta 1, the prior distribution we're going to induce on the treatment effect on mu1 minus mu0 is going to have variance delta 0 plus delta 1. Right? So the prior variance on the treatment effect is going to be larger than the variance on either of the two group means individually. So if you stop and think about this, this is a little bit weird, right? So we're saying that we know less about the plausible magnitude of the treatment effect than we do about the plausible range of the outcomes in either treatment arm. In a lot of contexts, I'm going to claim that's a little silly. And in particular, in the context of an educational intervention like the one I just described, we actually know a lot about the plausible distribution of treatment effects. We know that it sits right around a big fat 0, and we know that the spread is very, very small. Okay? Most of the things we try to do in education are not effective, on average. And the things that are effective are not doing huge things, presumably they're possible. Okay? So in my particular context, and I would claim in a lot of scientific contexts, we actually know more about tau than we do about mu0 or mu1. Okay? So what do we do? Well, if you have the good fortune to take an intro-Bayesian class, particularly if you have the good fortune to take an intro-based class at a Sterling institution like this one, you know what to do. Right? So we reparameterize our model. Okay, so I can rewrite the model equivalently as just the same two groups model, except now I'm going to parameterize the model in terms of mu, which is going to be the expected outcomes under control, and tau, which is going to be the treatment effect. So my expected outcomes under treatment are just mu plus tau, right? So the parameter of interest here is still tau. That's still going to give me the average treatment effect. But that's the thing that I want to know. Now it's a model parameter, and I can put a prior distribution on it directly. Right? So I can specify particularly that that thing should be centered at 0. I can think carefully about what that prior variance should be. Or I can specify some defaults that I think are going to do something reasonable, and then I can proceed from there. Okay? So again, if you're sort of familiar with Bayesian inference, this is a natural thing. We do this all the time to parameterize models in ways that are convenient to us, so that we can think about prior distributions and their implications. This is not something that happens in nonparametric modeling for causal inference. Okay? So how does this relate to models where we're trying to infer heterogeneous treatment effects? Well, the leap is sort of obvious, right? So the first thing that you might think about doing when you're writing down a nonparametric prior for heterogeneous treatment effects would be to say, all right, so I've got two treatment arms. I'm going to have the mean now depend on x, right? And I'm just going to have f naught for the control group, f1 for the treatment group. If I'm interested in the treatment effect, I just take f1 of x minus f naught of x, and that gives me my parameter tau of x, and I'm good to go. Okay? The problem here is the same as it was before. Right? So we have no direct prior control on that tau of x parameter, right? We have to sort of bank shot it by what we specify for either of the treatment arms. And all sorts of things can go wrong, right? So in particular, we could have a simple form for f1, a simple form for f naught, and they could compose to make something that's actually a little bit more complex. Right? So regularizing each of those treatment arms individually is not necessarily going to do what I want. The other problem that I have here is that all the variables that are in my model are necessarily potential treatment effect modifiers. Okay? That's a problem for me in the context of the mindset study because we actually collect a lot of information at baseline about schools and students that are not plausible treatment effect modifiers, but I would like to have them in my model to reduce the residual variability for power, basically. Right? This isn't going to do what I want. The next thing you might think to try is just say, well, all right, I've got some complicated, I've got some Bayesian nonparametric prior I'd like to use for f. Maybe I can just take that treatment effect, the treatment assignment indicator, just sort of concatenate it out of my covariates, and now I've taken this causal inference thing, I've turned it into regression, and I'm good to go. Now if I want to compute the posterior distribution of tau of x, well, what do? Well, I get a posterior distribution for that function f of x and z. I plug in x, comma 1, I plug in x, comma 0, I take the difference, and now I have tau of x, I have my conditional average treatment effects. Okay? I really haven't solved my problem, right? I still have no direct control over that function, right? I have no direct prior control over that. For a lot of nonparametric priors we might like to use on f, we actually don't really know what the prior distribution on tau of x is going to look like. Okay? In particular, for something like Bayesian additive regression trees, I have no idea what that induced prior looks like, except I know that it seems to do something reasonable. I also still have the problem that every variable in x is still a potential treatment effect modifier, right? I have no way to say that some of these variables are only sort of determining the level of y and not the effectiveness of treatment. Here again, the solution is pretty straightforward, pretty intuitive, fairly obvious, I think, right? We just reparameterize the model again in terms of the heterogeneous treatment effects, right? So now I write my outcomes as y equals mu of x plus tau of w on a subset of x times that treatment effect indicator z plus some errors. Right? Now in this model, my heterogeneous treatment effects are given to me by tau directly. I can think about a prior distribution on tau that makes sense, whatever that means to me, and regularize that independently of what's going on of the control for confounding or the incorporating variables for power purposes. So in our paper, we used independent BART priors on mu and tau. I don't really have time to tell you what BART is, except that it's awesome. But all the points that I just made are sort of generic. They're not really specific to trees at all. Right? If we're thinking about writing down a prior distribution model for heterogeneous treatment effects, we should really be thinking carefully about how to specify that prior. Okay? So we made a bunch of adjustments in this vein, right? So the original BART paper made a bunch of proposals for how we would use BART in the context of prediction. We adapted these for our context, where we thought that heterogeneous treatment effects were going to sort of vary less than predictions might. Okay. Not really going to go through that. What happens with observational data? What changes? Well, not much, right? I mean, if you have a randomized controlled trial, if you have an observational study, if you have anything where you're writing down a complicated Bayesian model, I think it's a good idea in principle to isolate the parameter of interest and think very, very carefully about the prior you're reducing on that. Okay? One thing that we do propose doing for an observational study is to actually include an estimate of the propensity score in your model over here. There's a lot of reasons to think that's really important. I don't have time to talk about them today, but we have some Some rationale for that in the paper, we have lots of independent evidence that this is important too. Okay, so these are studies where we didn't design data generating processes, but this seems to show up as an important way to actually make better estimates of treatment effect heterogeneity. Okay, so let's come back to the national study. So what I'm going to show you today is a new analysis of the effects on math GPA in the overall population of students. Okay, so we published on this data set before. I'm showing you a slightly different analysis here. We have basically three interesting potential treatment effect modifiers. Those include the baseline level of mindset norms, so sort of the overall level of mindset beliefs in the schools before we did the intervention. School achievement, which is a complex composite of things that you would expect, test scores, graduation rates, those sorts of things. And minority composition. Okay, minority composition primarily in there as a control. Okay, so we want to sort of understand whether there's heterogeneity by these two variables controlling for minority composition. And we have a whole pile of other controls, things that we measured about students in schools at baseline. Slight hiccup here is that we actually have students randomized nested within schools. We do sort of the obvious thing to modify a multi-level linear model to accommodate that structure. So we're not going to get sort of tricked by having error distributions or residual standard errors that are too small. But here again, I'll just remind you guys that we have three treatment effect modifiers and a bunch of controls. And three treatment effect modifiers are collected in that vector. School achievement, baseline mindset norms, and minority composition. Okay. And then the question becomes, we fit this model, and now what are we going to do with it, right? So one of the great things about Bayesian inference is that we can get posterior distributions for about anything. If you can compute it, you can get a posterior distribution for it. One of the drawbacks of Bayesian inference is that you can get posterior inference for just about anything, right? If you can compute it, you can get a posterior distribution for it, right? So we have to sort of decide what to look at. So we can estimate treatment effects for schools, for the population, for the sample. We can estimate treatment effects for individual students. We can go all up and down that ladder. But our collaborators had two sort of specific scientific questions for us. The first one, for which groups was the treatment most or least effective? Okay. So our model has sort of continuous-ish patterns of treatment effect moderation. That's actually pretty hard to summarize and distill for somebody. Okay. So when we're thinking about communicating treatment effect heterogeneity, some kind of subgroup analysis can actually be really effective. Okay. And then the second bullet, which there's absolutely no chance I'm going to get to, is what is the impact of positive treatment effect modifiers holding some of these other modifiers constant? Okay, so I'm not going to get there, but maybe we can talk about that later. So our approach to this question of subgroup finding is to treat it like a Bayesian decision problem. It is a Bayesian decision problem. I'm sitting in my office. I have to decide what I'm going to go and show to my collaborators. Okay? So I know a couple of things. I know that if I go in there and I have 15 different subgroups, it's going to be very difficult to talk them through that. Right? So I would like to have a relatively small number of subgroups to report. And then just sort of generically, if we think about subgroup finding as a problem, what we would like is we'd like to find sort of buckets that are going to maximally separate students into subgroups, right? Based on the average within those buckets. So the way we think about doing that is choosing subgroups represented by a recursive tree. That's easy to look at, easy to explain. We want that recursive partitioning tree to be relatively small, so we don't want there to be a whole lot of subgroups. If you care to write it down formally in math, you can do that, right? So we have sort of a squared error approximation for the subgroup means to the true function that we estimated. We have a complexity penalty that basically says how shallow is that tree, how deep is that tree rather. But what we can do is we can actually solve this Bayesian decision problem to give me a recursive tree partition, and then I can look at posterior distributions of conditional average treatment effects inside of those buckets. Okay? This is all sort of statistically kosher, right? So we're solving a proper Bayesian decision problem. We're looking at the posterior distributions within these subgroups. We're using the data exactly one time to move from the prior distribution to the posterior distribution. So if we do that, we end up with pictures that look something like this. Okay? So this is the recursive tree that I estimate, the recursive partition that I estimated. The first cut that we make is on school achievement. We make that cut at about the 67th percentile. Okay, so those are estimates of population quantiles, my cut points. And what happens is we sort of work our way down the tree. If we make that first cut sort of separates schools into high achieving schools and lower achieving schools. In the higher achieving schools, we estimate very small conditional average treatment effects. Okay, so conditional average treatment effects that are about 0.01. The average treatment effects in the whole population here is about 0.04. Okay? We can keep going down the tree. So if we keep going down the tree, the next cut that we make is on baseline levels of mindset norms in the school, and that happens at about the median. Okay? So we take that group of lower achieving schools, And then we separate them into low norm schools and high norm schools. If we look at the lower achieving low norm schools, we get a point estimate for conditional average treatment effects that's about 0.032. Conditional average treatment effect in the lower achieving high norm schools that's actually much larger, it's about 0.073. Okay? So it looks like we have sort of meaningful treatment effect heterogeneity here, which is good. It's in the same directions as was pre-registered in the analysis plan for the National Mindset Study, although we didn't need to pre-register anything when we did this analysis here, right? This is all just sort of, we have the posterior distribution. I get posterior distributions for those conditional average treatment effects. Those are the density plots on the right. So in the gray is the posterior distribution, the average treatment effect, and then the colors match the subgroups in the tree. Okay? So we can go on and ask other questions, like what is the posterior probability that the high norm schools have a higher conditional average treatment effect than the low norm schools? We can actually estimate the whole posterior distribution of that difference. We don't have to reduce it to a number. Some people like to see the numbers. If you want to see the number, it's there, the posterior probability that the average treatment effect in the lower achieving high norm schools is bigger than the lower achieving low norm schools, is about 0.93. Okay. So that's the alarm. There are tons of other summaries we can do. I don't have time to talk about any of them, but many of them appear in these papers, and I'm happy to talk about stuff in the quiz and things like that. Thank you so much for coming.
I only have about a minute or two for questions. You said that your response was the math GPA.
Yeah.
And I imagine that at Bronx Science High, about 15% of the students get an A.
Yep.
And Githens, which is a terrible school here in Durham, about 15% of the students get an A in math.
Yep. I think that's the first order effect of what you're seeing in the green.
Okay.
Yeah.
But
if you look at other outcomes, if you look at outcomes like taking advanced math, taking more advanced math courses, that moderation goes away. You actually start to see treatment effects in some of the higher achieving schools.
okay, I was concerned that you might not have a durable measure of math achievement.
We have different measures, yeah. So the challenge seeking, do they take advanced math? I think that's a more relevant measure. And then we are following these things over time, so we should know.
One more question. All right. Well, let's thank the speaker again.